This video will provide a brief introduction to circuits. It is important to note that this is a continuation of a previous video. This is a part 2, and as such, if you have not watched the first video, I would recommend you doing so before watching this one. And without further ado, let's begin the lesson. So, I find it useful to first begin with a review of the previous lesson before jumping into the new stuff. And this video will focus on, at least the new stuff will, on solving more circuit problems. This last video, we learned about voltage, which was defined as the amount of energy per charge. And we also know this as potential difference. Current was also defined, and it was defined as the following. The amount of charge that flows past a point per time. And then after, we discussed Ohm's law, which is the following. Ohm's law states that the current between 2 points is directly proportional to the voltage across those points. And as such, the equation for voltage is found to be the energy that you have per charge. The current was found to be, in terms of equation, the amount of charge that flows past a point per time. So the equation is as such. Using Ohm's law, we came up with the equation which states that the voltage is going to be equal to the product of the current and the resistance in a circuit. So this equation is important. And with it, we will solve some circuit problems. So let's first write this equation in the top left corner, as it's quite important. So with this equation, we know that we can solve for one of these properties or one of these quantities if we know the other two. So let's say we had the following circuit. And we know that the amount of charge which flows past that point is 10 amps. Current is measured in amps, or at least that's the SI unit for current. The voltage, or potential difference, was 20 volts across the cell. what we can do is solve for the resistance. So using this equation, you can rewrite it. We can solve for resistance. We can plug our values in. So we know we have 20 volts. The current is 10 amps. So then we know that the resistance is equal to 10 ohms. So let's try solving another circuit. Let's say the current at this point is 5 amps, and this time we know the resistance. The resistance of this resistor is going to be equal to 5 ohms. And what we're asked to do in this problem is find the voltage across the cell. Now using the equation, we could simply rewrite it. Plug in our values for current and resistance. And if we multiply this out, what we find is that the voltage equals 25 volts. Now, you may have realized we're using two different V's. One for potential difference, or voltage, and then another for volts. It is important to note that these two V's stand for two different things. Usually, you will see potential difference written in italics. However, it's hard to handwrite in italics. So typically, you see the same symbol, and you have to discern the difference depending on the context. You may even see potential difference be written like so, with a U, or even change in U. In contrast, volts are not written in italic type. So now that we had some practice with circuits, let's move on to to resistance rules. You may have noticed we've only used one resistor in all of these circuits. But what if we had two resistors in series? Or maybe two resistors in parallel. What would we do? Well, luckily, there are some rules for resistors in series and for resistors in parallel that we can follow in order to find the resistance between these 2 points here and these 2 points here. For circuits in series, it's quite easy. All I have to do is add up the resistance of the first resistor and the second resistor. So if, for example, the resistance of the first resistor was, let's say, 4 ohms, and the resistance of the second resistor was 2 ohms, the total resistance, which we can denote as resistance T, would be equal to 4 ohms plus 2 ohms, which equals 6 ohms. In contrast, for parallel, it's a bit different. In fact, the resistance between this point here and this point here is lower than if we only had one resistor. In fact, the resistance between those 2 points is described by the following equation. The inverse of the total resistance is equal to the inverse of one of the resistors in parallel plus the inverse of the resistance of another resistor plus how many resistors you have in parallel. So in this case, only 2. However, this equation works for an unlimited amount of resistors in parallel. So for example, if this resistor here had a resistance of 2 ohms, the bottom one had a resistance also of 2 ohms, we can plug these values in the equation, get a result. So this over here going to be equal to 1/2 plus 1/2, which equals 1. And we can't write 1 ohms because remember, this over here is the inverse of the total resistance. In fact, in this case, it works out that since the inverse of the resistance is equal to 1, and the inverse of 1 is simply just 1, that we in fact can write the resistance between both points is equal to 1 ohm. However, if, for example, instead of 2, this was 4, and this was 4 as well, oh, I broke my circuit. There we go. If this was 4, and this was 4 as well, ⅓ plus 1/4 would equal 2/4, which equals 1/2. And then the inverse of 1/2 would be 2. And therefore, the total resistance would be 2 ohms. And if you want an equation for resistors in series, it's going to be the same thing as in parallel. However, you're summing the actual values of the resistance and not their inverses. And again, this works for an unlimited number of resistors in series and not only 2. And hence, that's the purpose of the extra plus. So if you follow these two equations for resistors in parallel and in series, you should be able to solve quite a few more circuits, and more complex ones at that. So I hope you enjoyed the video, and thank you for watching.